A smart grid is an electrical grid which includes a variety of operational and energy measures including smart meters, smart appliances, renewable energy resources, and energy efficiency resources. Electronic power conditioning and control of the production and distribution of electricity are important aspects of the smart grid. Smart grid policy is organized in Europe as Smart Grid European Technology Platform. Policy in the United States is described in 42 U.S.C. ch. 152, sub. IX 17381. Rollout of smart grid technology also implies a fundamental re-engineering of the electricity services industry. Although typical usage of the term is focused on the technical infrastructure. Background. Historical development of the electricity grid. The first alternating current power grid system was installed in 1886 in Great Barrington, Massachusetts. At that time, the grid was a centralized unidirectional system of electric power transmission, electricity distribution, and demand-driven control. In the 20th century, local grids grew over time, and were eventually interconnected for economic and reliability reasons. By the 1960s, the electric grids of developed countries had become very large, mature and highly interconnected, with thousands of central generation power stations delivering power to major load centers via high-capacity power lines which were then branched and divided to provide power to smaller industrial and domestic users over the entire supply area. The topology of the 1960s grid was a result of the strong economies of scale. Large coal, gas and oil-fired power stations in the 1 gigawatt to 3 gigawatt scale are still found to be cost-effective, due to efficiency-boosting features that can be cost-effective only when the stations became very large. Power stations were located strategically to be close to fossil fuel reserves. Siting of hydroelectric dams in mountain areas also strongly influenced the structure of the emerging grid. Nuclear power plants were sited for availability of cooling water. Finally, fossil fuel-fired power stations were initially very polluting and were sited as far as economically possible from population centers once electricity distribution networks permitted it. By the late 1960s, the electricity grid reached the overwhelming majority of the population of developed countries, with only outlying regional areas remaining off-grid. Metering of electricity consumption was necessary on a per-user basis in order to allow appropriate billing according to the level of consumption of different users. Because of limited data collection and processing capability during the period of growth of the grid, fixed tariff arrangements were commonly put in place, as well as dual tariff arrangements where nighttime power was charged at a lower rate than daytime power. The motivation for dual tariff arrangements was the lower nighttime demand. Dual tariffs made possible the use of low-cost nighttime electrical power in applications such as the maintaining of heat banks, which served to smooth out the daily demand, and reduce the number of turbines that needed to be turned off overnight, thereby improving the utilization and profitability of the generation and transmission facilities. The metering capabilities of the 1960s grid meant technological limitations on the degree to which price signals could be propagated through the system. Through the 1970s to the 1990s, growing demand led to increasing numbers of power stations. In some areas, supply of electricity, especially at peak times, could not keep up with this demand, resulting in poor power quality including blackouts, power cuts, and brownouts. Increasingly, electricity was depended on for industry, heating, communication, lighting, and entertainment, and consumers demanded ever higher levels of reliability. Towards the end of the 20th century, electricity demand patterns were established. Domestic heating and air conditioning led to daily peaks in demand that were met by an array of peaking power generators that would only be turned on for short periods each day. The relatively low utilization of these peaking generators, together with the necessary redundancy in the electricity grid, resulted in high costs to the electricity companies, which were passed on in the form of increased tariffs. In the 21st century, some developing countries like China, India and Brazil were seen as pioneers of smart grid deployment. Modernization opportunities since the early 21st century. Opportunities to take advantage of improvements in electronic communication technology to resolve the limitations and costs of the electrical grid have become apparent. Technological limitations on metering no longer force peak power prices to be averaged out and passed on to all consumers equally. In parallel, growing concerns over environmental damage from fossil-fired power stations has led to a desire to use large amounts of renewable energy. Dominant forms such as wind power and solar power are highly variable, and so the need for more sophisticated control systems became apparent. To facilitate the connection of sources to the otherwise highly controllable grid, power from photovoltaic cells has also, significantly, called into question the imperative for large, centralized power stations. The rapidly falling costs point to a major change from the centralized grid topology to one that is highly distributed, with power being both generated and consumed right at the limits of the grid. Finally, growing concern over terrorist attack in some countries has led to calls for a more robust energy grid that is less dependent on centralized power stations that were perceived to be potential attack targets. Definition of smart grid. A common element to most definitions is the application of digital processing and communications to the power grid, making data flow and information management central to the smart grid. Various capabilities result from the deeply integrated use of digital technology with power grids. Integration of the new grid information is one of the key issues in the design of smart grids. Electric utilities now find themselves making three classes of transformations. Improvement of infrastructure, called the strong grid in China, addition of the digital layer, which is the essence of the smart grid, and business process transformation, necessary to capitalize on the investments in smart technology. Much of the work that has been going on in electric grid modernization, especially substation and distribution automation, is now included in the general concept of the smart grid. Early technological innovations. Smart grid technologies emerged from earlier attempts at using electronic control, metering, and monitoring. In the 1980s, automatic meter reading was used for monitoring loads from large customers, and evolved into the advanced metering infrastructure of the 1990s, whose meters could store how electricity was used at different times of the day. Smart meters add continuous communications so that monitoring can be done in real time, and can be used as a gateway to demand response-aware devices and smart sockets in the home. Early forms of such demand-side management technologies were dynamic demand-aware devices that passively sense the load on the grid by monitoring changes in the power supply frequency. Devices such as industrial and domestic air conditioners, refrigerators and heaters adjusted their duty cycle to avoid activation during times the grid was suffering a peak condition. Beginning in 2000, Italy's Telestore project was the first to network large numbers of homes using smart meters connected via low-bandwidth power line communication. Some experiments used the term broadband over power lines, while others used wireless technologies such as mesh networking promoted for more reliable connections to disparate devices in the home, as well as supporting metering of other utilities such as gas and water. Monitoring and synchronization of wide area networks were revolutionized in the early 1990s when the Bonneville Power Administration expanded its smart grid research with prototype sensors that are capable of very rapid analysis of anomalies in electricity quality over very large geographic areas. The culmination of this work was the first operational wide area measurement system in 2000. Other countries are rapidly integrating this technology. China started having a comprehensive national WAMS system when the past 5-year economic plan completed in 2012. The earliest deployments of smart grids include the Italian system Telestor, the mesh network of Austin, Texas, and the smart grid in Boulder, Colorado. See deployments and attempted deployments below.